All right, start streaming. So a few interesting things. This is actually okay. Maybe this is better. Um, I found another really cool Chrome extension. Depending on your browsing habit, if you like to open a lot of tabs like I do, this one works out kind of really well for me. It's called. Let me drag it down a little bit. It's called Tabs Outliner, and it can display all the tabs that you have opened, along with which window has which one. If you open a new tab from an existing tab, it actually is hierarchical. It can show you your history of browsing. It can come in handy, if you need to do some research, like learning a new programming language, or you're looking up references for whatever class you're studying. So this can help keep track of all that stuff. But it can also remember previous sessions. So if you close your browser or your computer crashes, it can actually maintain a history of your browsing of your tabs. So you can actually go back in time and find out, oh, okay, I was in the middle of doing something, like I was learning how to use Java for blah, blah, blah. And you can reestablish that context by using this tool. Whatever you save can also be saved to your Google Drive. So now you can sync across multiple devices and whatnot. So I would not do anything that is kind of sensitive in terms of security with this tab. But for homework, doing research, learning a new programming language, researching on math problems and whatnot, I think it's great. It works really well with my with the other extension that I use, which, let me see, is this one here, the Great Suspender. So these two work really well, with each other. One will basically suspend a tab when I don't use it for too long, to save not only memory but also processing time. So if you bring your laptop computer to school and you don't recharge your computer, often, and you need to run on battery and you want to minimize how much energy is spent, this I find that this tool really helps to reduce processing resources. So your mileage may vary. Keep that in mind. All right, so with that out of the way, we are going to go through a practice exam, because next Wednesday is really the time for our first exam. So what we'll do today is to go through a practice exam, which is actually the exam from last semester. So this is the same exam one as the fall semester of 2018, but I use it as a practice exam for this class. Are there any questions about? Nope. Okay. So if you go to announcements, I just sent it this morning. And last week I was sick, otherwise I would have mentioned this also. So there's a PDF. Just go ahead and open the PDF. And we'll use this, for practice purposes. So the first thing you want to kind of keep in mind is, don't wait until the last moment to put in your name at the end of the test. Write down your name first, okay? I don't understand why people do not do that first. Because if someone forgets to write down the first and last name, I don't know whose exam it is. So don't run that risk. Much of this is still applicable other than the time and the date. The exam allows you to bring any type of material that is either handwritten or printed prior to the test. So that includes all the modules that I have written. It includes your own hand notes. Okay, some of you take notes during class. Yeah, go ahead. You can bring the whole notebook. Yep. If you find discrete math textbooks somewhere else in the library, or a friend of yours has one and you find it useful, you can bring that. You guys can work together to study for the test. As long as the material is prepared prior to the test itself, it's okay too. You can go through my videos, and in a particular screen, if I have an example that you feel, oh, okay, I want that, to be, available, you can take the screenshot, print it on a piece of paper, bring it with you. So anything that is printed or handwritten prior to the test on paper is going to be okay. No electronics during the test, other than a simple calculator. I don't think you'll need a calculator for this class, but if you feel better with a calculator, you can bring a scientific calculator. A graphing one is fine too. I don't really think the graphing part is going to be useful at all in this class, but if you feel that, that's my only calculator, you can have a calculator with you as well. So are there any questions about what you can bring to the test next Wednesday? Because today is the practice test, so 1 week from today is the actual test. No questions? Okay, moving on. The test is an individual exam, which means the score of the test should only reflect the competency of the person with the name on the test. Okay, so I know everybody knows this already. It's just that I need to emphasize that. No sharing of open book or notes material during the test. So if someone sitting next to you says, I forgot to bring blah, 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 and I see that you have that, can you share with me? Not during the test. Okay? So every person is responsible for his or her own material, for the test. And, I cannot let people share material during the test. Is that okay? Now, before the test, okay, if the other person says, I'm pretty sure I got this already, I don't really need this note, and you can have it. As long as that is done before the test, it's okay. It's just no exchange of material or media during the test. Do not talk about the questions with anyone who may not have taken the exam. So it's just in case somebody is sick, I don't want that person to have any knowledge of the questions. You might want to bring additional sheets of paper. Binder paper works really well, just in case you need more space for the questions. I will give you space to write on the exam itself, but if you think that you might need additional space, then bring your own paper. Okay? And on that paper, on any sheet of additional paper, make sure your name is on it, and also the number of the question is also on it. Because I don't want to look at a loose piece of paper with some numbers and go like, okay, whose answer is this to what question? I will also bring a stapler, and I think a stapler is already here, so we can use that stapler to kind of put everything together. Write legibly. Make sure that I can read your handwriting. I know that is subjective to a certain degree, but just try your best penmanship when it comes to making it clear. So no need to make it fancy, just make it clear. Also, make your answers as complete as possible. The idea of making your answers as complete as possible to reflect your thinking process is so that if there's partial credit, I can give you partial credit if the final answer is wrong. On the other hand, if someone just gives me an answer with no steps to derive the answer and the answer turns out to be wrong, then I cannot have any way to assign partial credit because I have no idea what process that person goes through to get to that wrong answer. On the other hand, if the steps are clear and most of the steps are actually correct, but for some reasons the actual final answer is wrong, I can say, well, I can see this person actually knows how to solve the problem, have the knowledge, and just by making a simple mistake somewhere the answer is wrong, I'll give that person partial credit. So that's why you want to make your answers complete and write down your reasoning in your answers. Not just the final answer, but your reasoning as well. Some questions may cross pages. I try to avoid that with the typesetting tool that I have. But just in case, okay, make sure that you do not read only one half of a question if it crosses pages. The exam accounts for 20% of your final grade. So is all the homework assignments added together. So is exam 2. The final exam is 40% of your grade. So do we have any questions about all of this? I'm also going to I'm inclining to also keep this one, all questions have equal weight. So that makes it easier for you guys to evaluate which question should I tackle first. Because, you probably already know the trick. Go through all the questions. If they all carry equal weight, whatever seems easiest to you, start with that one. So you always leave the most difficult questions last, assuming all questions have equal weight. If they're not equal weight, then it gets difficult, because now you have to kind of balance how much time do I need to answer this really simple question, but how many points am I getting out of this simple question? But by making all the questions equal weight, it's easy, right? You just look at each question, whatever seems easiest to you, start with that one. So do we have any questions before getting into number 1 of the practice exam? No questions? Okay. Then we'll move on to question number 1. So question number 1 of 6 says, you are given, a set A has the following elements, blah, 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 blah. We are also given, and B is that. Okay, so you're given this conjunction is true. Okay, it is an assertion that A does have the following elements and B does have the following element. Compute and write the values of the following expressions. So now you have to give me the answer to each and every single one of these. So what I'll do is I'm going to I'm not going to write on this. I'll write on the side of this using a text editor. Okay. All right. So I'm going to repeat the question here. A union B is going to be what? Well, it has everything in A and everything in B, but no repetition. That's the thing. So we got 12, 29, 8, 2, 6, and then we have 9, 6 as a set, and then a 9 and a 6 after that. Now, order is not important, okay? If someone wants to say, Tag, these numbers are not sorted. I cannot deal with numbers that are not sorted. By all means, go ahead and sort the numbers. I don't care, okay? Because items inside the curly braces of a set is order independent, okay? So, yeah, go ahead. Repeat 6. Oh, you're right. Okay, I forgot. I missed that one. Thank you. So that would be wrong. If I have 2 6, I would get partial credit deducted because you cannot have repetition of the same value in a set. But this would be correct, okay? So 6, 9 appears as individual elements of the union, but 6, 9 or 9, 6, however you want to call that, as a set, is also an element of the set. Okay, so keep in mind that one particular element, a element in a set, can be by itself a set as well. So are we doing okay so far with A union B? Okay. Okay, next sub-question is A intersection with B. So that would be all the elements that are common to A and B, right? So there's only 6 here. 9 is not, okay? So number 3, the third sub-question is, okay, so the first 2 questions, have an answer of a set, right? The third one is not, okay? The third one is either true or false. So the third one is asking, is A a subset of B? The answer is no. So we say false. If you say no, I would take it as an acceptable answer too, but it's better to say it is false. Or 0, okay? If you give me a 0, I would interpret it as false as well. All right, next one, B is a subset of A. It is also false. Why is it false? Okay, because 9 is in B, but not in A. But 9 is in one of the elements of A. That doesn't count. It has to be at the top level. You cannot look at the nested values inside other sets that are embedded into A. Okay, so this is important. Next one is A minus B, or the difference between A and B, which are things that are in A but not in B. So we got a pretty long list. Yes?
You said, this is a hypothetical, but if you said B was a subset containing, or not subset, but was a set containing the set 9, 6, right? So like you just have an extra curly brace around what's already there for B. Then would B be a subset of it?
You mean like this?
No, I mean like on the right-hand side of the equation.
On the right-hand side.
Where you define what B is, right? You say B is...
Where I define B, you mean like here?
Yeah, so you put another curly brace around that, so then you just have the...
If B is that, then B would be a subset of A, and then their intersection would be 9, 6 as a set, but also in addition 6 itself.
So the nested counts for...
Oh, right. So 6 is not. 6 is not. Yeah. Okay. So 6 is not because because we put the curly brace around the entire thing already. Okay. Gotcha. Okay. So A minus B is what is in A but not in B. So it's kind of like the union, kind of like A but without whatever is in B. A minus B? Yeah, the only thing you get rid of is 6. But that means everything else in A is in the difference. Right. So we have, you still have to enumerate, all of those. So 2, 6, 6 is gone. But 9, 6 is there. So that would be the difference. The next one is A is an element, so we can just say A in B is false. And then the other one is B in A is true. So a question like this, is really just to test whether you understand the symbols. There's not really a whole lot of computation that you have to do. It's just a matter of, do you know what is a union, an intersection? But you also have to know what each operator will give you as an answer, as a type. Okay? Does it give you a set as a type? Does it give you a Boolean as a true-false answer? That you have to determine as well. So do we have any questions about number 1 of 6? Yep.
In the top part where it says A equals that set, and you have the caret symbol.
You mean here?
Yep, to the right a bit. In between that and the caret.
This one? That's conjunction.
So conjunction, does that have anything to do with the way you're going to evaluate these expressions?
It is part of the assumption. So you are given, which means you are told that this is true. So what is true? Well, A has these elements and B has these elements. So the conjunction itself is true. So we know both equality holds true, basically. So that's why I use a conjunction, because if I use an or, that means, I know at least one of these two is true, but I don't know whether they're both true or not. So I have to use a conjunction to emphasize that both of those equalities are true. And that's a given. Sure. So are we good on number 1? Are there any additional questions about number 1? Okay, basically just a test of, symbols. So this is question number 2. So question number 2 says you are given that X as a set has 3, 19, 24, 4, 11 in a set. You are also told that 19, 24 as a tuple, 4, 11 as a tuple in a set is a subset of R. In addition, you're also told that R is reflexive and symmetric. So don't jump to the conclusion and say it is not possible. Why? Because what I have listed here is only known to be a subset of R. It is not equal to R. Okay? So the difference is we know at least these two are in the relation. Can there be additional elements in R? I didn't say anything, right? I did not say you cannot have additional elements. I only said that these two must be in R. So first indicate whether such a relation R is possible. What is possible again? Well, X equals to this. this is a subset of R, and R is reflexive and also symmetric. Is that possible? Absolutely possible. Is that okay? Now, if I change this subset of to equal to, then the answer is no. Okay, but it's not, right? It is subset of, so it is absolutely possible. So you have to indicate, yes, it is possible. And if so, present an example of such a relation in the form of R equals to curly brace, blah, 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 and then close it. If not, you have to explain why it is not possible. So since we already know it's possible, we just have to enumerate what is in R in this case. So in this particular question, R is a set. Okay, so I'm going to use the long format here. And then the relations in here, because it has to be reflexive, so that means 3, 3, 19, 19, 24, 24, 4, 4, 11, 11, they all have to be here in order to be reflexive. But because it is also symmetric. Now, if it is symmetric, that means if 1924 is here, 2419 has to be here too. Okay? If 411 is here, 114 has to be here too. But then what about 244? Well, if 244 is not here, then 424 should not be here either. So that's how it is symmetric. Okay? So if you don't want to kill yourself to make this, a larger than it needs to be type of set, then you just have to add whatever is needed to it. So these two have to be here, and then these two also have to be here. So this is the minimal relation to meet all the requirements. Now, if you want to say, but I also want it so that between every single element, there's also a relation, and they also have to be symmetric. By all means, add additional elements. But if in your process of adding additional elements, you forget something and you say, okay, I'm just gonna add I don't know 3, 11, and you lost track of what is already in here, and you forget that 11, 3 also has to be here, then your answer will be marked wrong. So just do the minimum to make it meet all the requirements. Don't do any additional work because it's not worth it. So this would be the correct answer. This would be the minimum set to meet all the requirements of question number 2. Okay, so are we good? So if this is the answer, how do I show additional work or reasoning and stuff like that? Well, you can quote what it means to be reflexive. Okay, go to the notes and just kind of quote, reflexive means da 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 da. Okay, now, is it going to be helpful? I think so. I mean, because if you mistakenly thought that reflexive is symmetric or the other way around, by writing it down, you go like, oh, okay, I'm just copying from text note, but this is not what I thought it was. Okay, so that might be helpful already from that perspective. If you write it down, I can give you partial credit, just by saying, okay, this person can identify what it means to be reflexive and what it means to be symmetric. So even if your final answer is not entirely correct, I can still give you partial credit by saying, okay, but I know this person knows the definition. It's just that, somehow the final answer did not include all the elements or have something that is in addition to what needs to be there. So are we good so far with number 2? Are there any additional questions about number 2? Okay. Let's move on to question 3. Okay, question 3 is about functions. Okay, so the question is giving you that the domain is known to be D, which has 6, 11, 17 as elements, and just like the previous question, I'm giving you a subset of F. So we know that 6, 17, 11, 11 is a subset of F. And we assume that D is a domain, E is a codomain, and F is known to be a function. Okay, how do we know that? Because we make that assumption. So you have to know how to read that notation. That notation says f is a function. It is an assertion that f is a function already. D is the domain, and E is the codomain. So immediately you have to be able to remember what it means to be a function. A function is a subset of the Cartesian product between the domain and the codomain, but there's one more thing that is needed for f to be a function. Every element in the domain has to map to one and only one thing in the codomain. That is a requirement. So by asserting this, we know that property of f already. So now I want you to define f and E as sets based on the stated constraints. This is part of the constraint, this is the other constraint, and this is the last constraint. Okay? If multiple answers are possible, just pick one. Okay? I don't need you to give me all the possible ways to arrange the set f and the set E to meet all the constraints. If a case is not possible, explain why it is not possible. Otherwise, your answer in each case should spell out the membership of the sets. So you have to spell out what is in F and what is in E. So there are 4 cases. The 4 cases are here. F is injective and surjective. F is injective but not surjective. F is not injective but surjective. And then F is not injective nor surjective. Okay? So we'll work on those 4 cases. So we'll work on the first one, injective and surjective, which is otherwise known as bijective. So in this case, f as a function, as a set, needs to contain 6, 17, 11, 11, oops, parentheses. And we also need to map 17 to something. Then you go like, what can it map to? Well, I have never spelled out any constraints on E. So E can have any element you want. Okay? So I can just say, well, maybe it will just have 0 in E. That's perfectly okay. And then E itself, is really just 17, 11, and 0. It contains all the values that are the second item in the 2 tuples of F. So are we doing okay so far with this answer at this point? Just to address bijective. Yep.
Would 6 also work?
You mean changing this to 6? Yeah, it'll work. But I can tell you what is not going to work, okay? You say 17 maps to 11. That is not going to work, because then we have 2 elements of the domain mapping to the same thing in the codomain. It is no longer injective. I can also tell you what is not going to work. This is already working, but somebody says, but I can just give you more items here. So instead of just 17, 11, 0 in E, we'll just also have 1 and 2 and 3 and so on and so forth. That will break it too, because now it's not surjective anymore. Surjection means every element in the codomain have to be mapped to. Okay, so this is one example for the first case. Second case is injective but not surjective. So let's see, 6, 17. Okay, I am super lazy here. I'm sorry, but I can do this. A little harder, yes. You need a hand scanner and a hand printer and some Scotch tape. Oh, you guys cannot see the rest. Let me rearrange this a little bit. Give me a second to... There we go. All right, so next one. Not injective, but surjective. Okay, so that means things can map to the same, at least 2 things have to map to the same thing, and but we cannot have additional elements in the codomain, right? Okay, this one I'm going to start fresh. So now 6, 17 has to be there because this makes f a it meets this requirement. Okay, because we have to have those two in f, so we cannot change that part. So we have to have those two. But then you can say, we'll map 17, to 17, or 11. So either way works, doesn't matter which one there. Okay, but then E cannot have, all three elements. E, because it still has to be surjective. So that means E can only contain 17 and 11. Is that okay? So even if you are to use copy and paste, you kind of have to know which part you can copy without modification and which part you can copy and paste and without modification. So it's still kind of important to understand the concepts. So the last one is not injective and not surjective. Okay. So we'll start with what has to be there. Okay, we'll start with these. So in order for this not to be injective, I can just map 17 to 17 this time, okay? Just like last time. But I also have to make this not surjective, which means in addition to 17 and 11 in E, we just need something else. 0 is fine. Is that okay? All right. Cool? All right. Let's move on to number 4. So question number 4 has the same kind of format as question number 3, but this one applies to relations. So let me just read the question first. Assume R is defined over the set of all positive integers, such that for all x and y in the set, all the positive integers, x mod y equals to 0 if and only if xy is an element of R. Okay, so let's just focus on this. Oh, I cannot click it because it's a PDF. So let's just focus on this part here and try to understand, okay, what does that mean? Okay, the following sentence actually tells you what it means. But let's see if we can decode it first, okay? So the first part says, it's a quantifier. It says, pick any two values. And by the way, those two values can be the same, but just give me one value for x, one value for y. They can be different, they can be the same, but they have to be positive integers, okay? The following has to be true, regardless of how you pick the values for x and y. What has to be true? X mod y equals to 0 if and only if xy is an element of R. What does it mean when x mod y is a 0? X is divisible by y, or you can say x is a multiple of y, right? Y is a factor of x, okay? Those are all various ways of saying exactly the same thing. So x is a multiple of y if and only if xy is in R. So basically R is saying x is a multiple of y. Okay, that's what R is representing. Okay, that's what the next sentence says, right? First, spell out the membership of the set S. So now you have to look at this format and say, okay, what is this set here? What is this representation? It means every element in S has the format of it's a two-tuple where the first item has to be 42. Okay, you don't have a choice. Okay, the first element has to be 42, but the second element is a variable. So the second element can be any E such that the following is true. Okay, what has to be true? 42, comma, whatever is an element in whatever R that we just defined earlier. Is that okay? And so now the answer is, okay, first of all, tell me what is S. Express S and tell me all the elements of this set S. What do you think? So it's a little bit more than that, okay? So in this case, the set S is going to, they all have 42, right? So you can expect it to be like a whole bunch of stuff like that, for one. The second thing is, I would start with 42, right? 42 is divisible by 42. 42 is divisible by 21. 42 is divisible by, what is the next one that makes sense? 14 maybe? I'm just going down, in decreasing order. The next one down is going to be 7, I think. And then we have 6. And then we have 3, 2, and 1. That's it. Oh, okay. And move it around like that. Okay. So is that working? So part of what this question is asking is, do you understand this notation? Do you understand this notation? Okay? Do you understand what is mod? But Tech, you didn't spend much time in this class to talk about mod. Well, that's because cisp440 is a co-requisite of this class. And I know that 404 or 401 is the prerequisite of 430. So I make the assumption that you already know what a mod operator is. Is that okay? So now we have to say, is R reflexive? Why and why not? First of all, you might want to mention what it means to be reflexive in order to say that it is not reflexive. So it is, oh wait, is it reflexive? So is R itself reflexive? It's not asking about S, it's asking R. The question is asking, is R reflexive? Because we never mention anything of defining S over X, right? Or over Z plus. So the question is asking R itself, is it reflexive? It is reflexive. Every positive integer is a multiple of itself. So it is reflexive. Are we okay so far? Okay. Is it symmetric? It is not symmetric. Okay. Is it anti-symmetric? Now, anti-symmetric is the funny one, remember? Because anti-symmetric is basically asking, do we have a case where we have A are B and B are A, but A does not equal to B? So in this particular R, do we have something like that? The answer is no, we do not, which means it is anti-symmetric. If A is a factor of B and B is a factor of A and B must be the same thing. Yes? Say that one more time. Okay. So anti-symmetry is defined as, okay, A are B and B are A implies B A equals to B. And that has to apply to any way to choose values for A and B in the set X, or in this case, Z plus. It's in the definition in the notes, okay? Yep.
You were using like less than or equal as an example for that, right?
Yeah, you can use less than or equal to as an example of anti-symmetric, right? But that implication does not hold true for different ways of choosing A and B. It does hold true, sorry, I take it back. It does hold true for this particular R. So choose anything, choose any two values. Choose any two positive integers, okay? One is called A and one is called B. If A is a multiple of B and B is a multiple of A, does that imply A and B are the same thing? All right, well, then it meets that requirement, and therefore it is anti-symmetric. So you kind of have to know where to find the definitions. That will be very helpful in the test. Okay? Some of you do not like the way that I write because I sprinkle definitions all over the place, right? Okay? And you don't like to highlight your things all over the place. Make your own neat list of all the definitions then. with your own annotation next to it, your own understanding of that concept. Okay, so that way you don't have to flip through pages and pages and pages of stuff that you don't like to read. You only have one single sheet of very clean list of definitions that you wrote to begin with. I think that makes it easy to find stuff. Do you guys agree? I once took a class in San Francisco State University, computer science, and I was only allowed to bring one single sheet of paper to help me in a test. Now, you have to understand that I write very, very small, okay? And as a rule, I do not buy college rule, binder paper. And you go like, but everybody likes, college rule because you can fit more stuff in it. Except I have double density. If I use wide rule, I can fit 2 lines for each line on the piece of paper. That is normally how dense I write. So I go like, yeah, I can fit a lot of stuff on that page, where most other students just run out of space to write stuff. So I compile my own list of key concepts, ideas, things that I tend to forget, and things that are important. So I had to spend some time to really think about what to put onto that list and how to put it in the list so that it's easy to find, how to index things and whatnot. So during the test, do you think I needed that piece of paper? I did not. Because by putting all the thoughts into, oh, I wonder whether I should put this into the list and where I should put it and how I should put it, all that stuff is already soaking into my brain, while I was preparing for that sheet of paper. I ended up not actually needing that piece of paper. So I'm telling you this, just to tell you, that is a part of, studying. It's a part of preparing for a test, at least for certain people. May or may not work for you. Your mileage may vary. Okay? All right, so getting back to this. Yes?
I wanted to ask for how you were asking us to define S. Is that generally like how you're going to ask us to define sets for this kind of question, or would you do it in other ways too?
You mean how to define S here?
Yeah. Like, would you give us a relation and then like the thing you
Yeah.
want us to do the relation over?
Yeah, or I can say, find a subset of R such that da-da-da-da. So there's a variation of ways to ask those questions. The key is you have to understand all the different notations that we have talked about in this class, especially things that are equivalent to each other, so that you can say, oh, this is asking me about the same thing as that. Okay? All right. Fourth item is R transitive. In other words, I'm asking you, find me 3 things, or give me values for A, B, and C. Okay? If A is a multiple of B and B is a multiple of C, can we confirm A is a multiple of C? Okay, meets that requirement. Check. It is transitive. Okay? Next item, is R partially ordered? The answer is yes, it is partially ordered, because what does it take to be partially ordered? It has to be reflexive, it has to be antisymmetric, it also has to be transitive. This R turns out to meet all 3 requirements. Okay? Do I expect you to remember all those definitions? No. Do I expect you to know where to find in my notes where those definitions are? Yes. So that's kind of a clue of how to study. Okay, start with the knowledge. Last one, is R totally ordered? What separates partially ordered from totally ordered? Totally ordered, in a totally ordered relation, every 2 items have to be related one way or another. Okay, and that's why less than or equal to is totally ordered when it is defined over integers. Because if you give me any 2 integers, okay, one value for A and one value for B, A is less than or equal to B, or B is less than or equal to A, one of those 2 has to be true. Or they can both be true if they turn out to be the same value, but at least one of those 2 have to be true. Does it make sense? So you have to ask the same question about, is a multiple of. If you just choose any 2 positive integers, okay, Do I know A and B, okay? Can I confirm A is a multiple of B or B is a multiple of A? And at least one of these two have to be true. No. Let's just pick A equals 5 and B equals 3. Is 5 a multiple of 3? No. Is 3 a multiple of 5? No. Is the disjunction true? No. Well, then it doesn't meet that requirement. So it is not totally ordered. It is only partially ordered. So that's what question number 4 is really testing, is how well do you understand those concepts. Question number 5. I did not like the way it formats it. It just put in way too much spacing. And I think I was able to fix that later on, but I forgot about how I did it. Okay, but anyway, let's read the question just the way it is. I know it's a little harder to read. Assume G is a function. It maps natural number Cartesian product with natural number to just natural number, is as defined in the Aleph No module. Okay? So on Wednesday, I don't want anyone to ask me, what is the Aleph No module during the test? I will not answer that question. Not even with a glare. I'll just turn away, pretending nobody asked me that question at all. Okay? So, we know what a G is, okay? So the question is, show that, blah, 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 okay? What do we want to show? We want to show that, okay, choose values for x1, y1, x2, y2 from, as an element of n, okay? So each one of these is a natural number. So pick a natural number value for x1, x2, y1, y2, okay? Show me the following, okay? Look at the stack of parentheses. Show that is true, regardless of how you pick x1, x2, y1, y2. And you can use whatever is already factual, established facts, in the module. That's basically the key. So what do I want you to show? I want you to show that if x1 does not equal to y1, or y1 does not equal to y2, x1 does not equal to x2, or y1 does not equal to y2, that implies the g value of x1, y1 as a single coordinate does not equal to the g value of x2, y2 as a coordinate. How would you show me that? Huh? You can do by cases, but you don't have to go that far. You can do it by contradiction, but even that is going a little bit. You can use an established statement in the module and start with that. What do we know about G? It is bijective. And what is the one thing that we know about bijection? It has to be injective. Very good. Okay. It has to be injective. What does that mean? It means two different elements of the domain, they have to map to two unique values in the codomain, right? So if x does not equal to x, if x1 does not equal to x2, or y1 does not equal to y2, that means we're talking about two different elements in the domain. By the virtue of being injective, we don't even need to use bijective in this case. By virtue that G is injective, they have to map to different values in the codomain. Done. Is that okay? Yep.
So if you were like super lazy and we're just like, this is true because it's injective, would that get the whole point?
You have to mention that it is injective, but you also have to answer the question of why being injective leads to this conclusion. Okay. Yep.
So that's all you have to write down, with all that space.
Yep, that's plenty of space. The amount of space can be deceiving. Yeah, something that is like a two-liner, I give you like a whole page, making people think like, what am I supposed to do with the rest of this space? Yeah, you can include some pictures. Okay, question 6 out of 6. This is the last one from the previous year's exam. Assume X is 4, 9, 10, 15, 21, and the following is a subset of R, 4, 15, 15, 10, and 10, 9. Define R in the minimal fashion. So this time I want the minimal fashion, which means I don't want an extra element at all, okay? So that R is antisymmetric and transitive, okay? Your answer should be in the form of R equals 2, and then list every single element in R. That's basically what that format is. Okay, so let's take a look at this one. So now the question is, what does it take in order for a relation to be transitive and also antisymmetric? Let's worry about transitive first, okay? So we know that certain things have to be there. 4, 15, 15, 10, and 10, 9, they have to be in R because we know that forms a subset of R. But R can have additional elements. So now the question is, in order for R to be transitive, what additional elements do we need? What is transitive again? If A are B and B are C, then A are C, okay? And no matter how you choose A, B, and C, okay? So in this case, a 4 relates to 15, 15 relates to 10. So that means we need 4 to relate to 10. Okay? All right, so, but it's not done yet. We know 15 relates to 10. We know 10 relates to 9. So 15 has to relate to 9. So we have to add that one. But then, we also have to go all the way from 4 to 9, because 4 relates to 9 now. So we have to add that last one. That is a minimum set. Now, you have to double check and make sure that it is actually antisymmetric. Is it antisymmetric? Yep. How do we know it is antisymmetric? Yep. You cannot pick any two values where you cannot give A and B values such that A are B and B are A, but yet A and B are different. In fact, there's no symmetry at all, so it's not an issue. Not a single element here has a symmetric entry in the set. That's it. That was the entire exam last semester. Yep.
Can you explain what you did? So you took the subset and the domain elements of the tuples, and then map them to.
You have to rely on the definition of what is transitive. Okay, so the definition of transitive basically says, if you give me, I give you 3 variables, A, B, and C, and you are free to pick any values from X as A, B, or C. They can be the same, they can be different. I don't really care how you do it. But the statement has to be true. What statement are we talking about? A are B and B are C implies A are C. Has to be true. Okay? So then you say, well, what if I pick 4 as A, 15 as B, and 10 as C? Then the left-hand side of the implication is true. I better make sure the left-hand side is true too, right? Yeah, your right-hand side, yes. The consequent has to be true. So that means A, which is 4, R10, also has to be in the set. So that's how I know that 410 has to be added. And you just go through every single one of those, but after you add 410, then you have to also combine 410 and 109 to know that 4 has to relate to 9, so 4, 9 has to be added too. Because anti-symmetric is more of a filter. So, okay, you can choose either one, okay, but when you're trying to construct a set, constructively, and the set does not begin with any type of symmetry, you don't have to worry about anti-symmetry. Now, if on the other hand, it is already looking to be a little bit symmetric, then you have to start to think about, is it even possible to make it anti-symmetric? Is that making any sense? So if this particular set also has, let's say we have one additional element, which is 15,4, then you have to argue and say it's not possible. Because if it contains 15,4 also as a 2-tuple, then it is not anti-symmetric already. Then there's no way to make it anti-symmetric by adding additional 2 tuples. Yes? Say that one more time. A relation.
Yes, if it's not symmetric, does that automatically make it anti-symmetric?
Okay, let me think about it. So the question is, if a relation is not symmetric, does it automatically make it anti-symmetric? Let me rephrase it in mathematical terms. Basically what you're asking is, if R is not symmetric, does it imply it is anti-symmetric? Let me write it down on my notepad here, and then we'll try to answer the question. I really don't have it, prepared, but we'll see, right? Okay. So the question is the following true? Okay, R is not symmetric implies R is anti-symmetric. I think that is your question. And the answer is no. I can find a single counterexample to show that this implication does not hold true for every single relation. Because in order for this statement to be true, it means give me any R over any X, it still has to be true. That makes it a universal truth. Okay? But I can show you one example where it is not true. Okay, so I will show you X as 1, 2, 3, and I will show you R as a relation defined over X as follows. Okay, so we have 1, 2, and we have, it is not symmetric. Okay, so we have 1, 2, we have 2, 1, and then we have 2, 3. R is a relation defined over X. So now the first question is R symmetric? It is not symmetric. Because in order for it to be symmetric, 1, 2, 2, 1 is good. But we have 2, 3, we're missing the 3, 2. If we had 3, 2, that would make R symmetric. But lacking 3, 2, R is not symmetric. Okay? Okay, it is not symmetric. So R is not symmetric means that this part of the implication is in fact true. Are we good so far? So if the left-hand side of implication is true, we better make sure the right-hand side is also true. Okay? So now we ask the question, is R anti-symmetric? And the question is, the answer is, it is not anti-symmetric. Why is it not anti-symmetric? Because we have 1 R2 and 2 R1, but 1 does not equal to 2. So it fails that requirement to be anti-symmetric. So in this case, what we have here is something that is not symmetric, and yet it is also not anti-symmetric. It's neither. So that term anti-symmetric is a little bit tricky, right? Because if you take this to an English class, okay, then your English professor will say, oh, that's easy, because anti means not, right? So there's no need to define symmetric and also anti-symmetric, because anti-symmetric is just the same thing as not symmetric. Well, unfortunately, that understanding based on natural language is incorrect in the context of this class. Anti-symmetric has a very definite meaning to it in this class. So that's why it is possible for something not to be symmetric, but also at the same time not anti-symmetric, which will totally baffle your English teacher. But don't give it a try, okay? If you want to give that a try, leave my name out of it. Are we good so far? All right. So the key to prepare for the exam is you have to know the definitions. Okay, you gotta know where to find the definitions and understand the definitions. Okay. Now, once you understand the definitions, you can rewrite in your own words what it means to be anti-symmetric, what it means to be symmetric. You can bring examples. Okay. So one thing you can do is to bring examples. If you like what I have here, I'm not going to save the file and upload it to the server so you can just download it and print it out, but you can bring it, okay? I mean, you can just take a screenshot, copy and paste it into Word and then print it out. But anything that's on paper is okay for the test. So are we okay so far with the material for the test? Are there any questions regarding the concepts? So we'll be testing everything, including up to but excluding propositional logic. So none of the propositional logic stuff is going to be in exam 1, but we will have everything up to relations. Is that okay? All right, very good. So we got about 20 minutes, maybe 15 left, so we can continue to talk about propositional logic, unless you guys have questions about exam 1. Any? Yep, go ahead.
So propositional logic won't be on the exam, it's everything before that?
So everything before propositional logic will be on the test or within the scope of the test. Yep. Mm-hmm. But then you have to be prepared for questions where I combine concepts, right? So I can say, oh, by the way, the intersection between these two functions turns out to be this, okay? But this function is injective. Tell me what the other function should look like, okay? That can be one of those questions, okay? So I can give you multiple concepts that are not discussed in class, in conjunction, but they do connect. It's kind of like Lego pieces, right? We got this Lego piece, we got this Lego piece. In class, I explain, here's a Lego piece, it's a 2x4, it looks like it's this thick, and it can be used for this purpose and that purpose, right? And then I can show you another piece, it's like, okay, here's another piece that will allow you to turn something 90 degree, so that you can have, Lego pieces that are usually stacked up this way, but now you can stack it up in the other direction. Okay, I explain how that piece is. But in the exam, I can now have a question that involves different kinds of pieces. Then you have to remember how they can possibly connect and use that to solve the problem. So keep that in mind, okay? So that means, the best way to prepare is to thoroughly understand each and every concept, okay? Are we good? Yep.
Go over the answer number 5 again.
Number 5? You know that I could just replay the recording up to this point. Okay. So the answer to this question is simply to utilize the fact that G is bijective. It's stated already in the module that G is bijective, otherwise there wouldn't be a G inverse, right? So if G is bijective, it means it is also injective. If G is injective, then every 2 different elements of the domain have to map to 2 different values in the codomain. And that is what we want. I mean, that implication is already done. Mm-hmm. All right. Are we good? So, assuming that we are good here, let's go back to propositional logic. I really like this icon. It's cute. Looks like me most of the time. Except when people wake me up, I'm usually not smiling. There'll be fangs, and the eyes turns red. Maybe I should change that animation. That would be kind of interesting. You poke on that little icon, the eye opens up, it's red, and then fangs, will start to grow out of the mouth and go, "Argh." All right, so we are back to propositional logic. And so the next thing I want to talk about is resolution. Okay, so let's start with resolution. Okay, I know how much you guys like these proofs. Okay, so here's a proof in Boolean algebra. So now the first question is, what is this mess? Okay, so at any time, you can look at the material of any class, okay, not just this one, as a pine forest, okay? So you have the ability to focus all the way in to individual pine needles, and sometimes we need that. You can also zoom out to a branch, a tree, and then sometimes you want to look at the whole picture. It's like, okay, I see the whole pine forest. I cannot see the individual pine needles anymore, but I see the forest. So at this point, we'll look at the branch, okay? The branch basically says, blah, 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 is always true. Okay? Skip all the steps in between, and you just come to the conclusion is, this is always true. Wow. Okay. What is always true then? So now you zoom in a little bit, to start to look at some of the details, okay? So what this one says is phi or psi, okay? It's a disjunction, and not psi or rho, okay? Another disjunction. If these two are true, the conjunction guarantees, implies phi or rho. Okay. How many symbols are involved in this entire discussion? We got phi, we got psi, we got rho. There are only 3 independent variables. Each one is Boolean. Okay? What is the significance? What is the significance of this implication always being true? So that means if you can guarantee me this, I can tell you that has to be true. That has to follow. Because that's the job of implication, of an implication that is known to be true. How do we know the implication is true? That. Is that okay? Okay, fine, but there are many, many implications that are guaranteed true. Why is this one particularly important? Because there are certain implications that are always guaranteed true. Why is this one particularly interesting? Do you see how many variables we have on the left-hand side of the implication? Count. 3. How many are used on the right-hand side? 2. Oh, 1 disappears. It makes things simpler. Okay? What makes things simpler? Oh, if one thing is non-negated on one side, and it is negated on the other side, then it disappears. The rest concatenates. What do you mean by concatenation? Well, each one of these Greek letters, otherwise known as a schemata, can represent a huge, gigantic expression by itself. So that means phi can be a huge, long disjunction all by itself. It also means rho is the same thing. Can it be a huge, long disjunction all by itself? It doesn't matter. If you can find a pattern like this, then the resulting pattern has to be true. Is that okay? So that's resolution, okay? First thing we need to remember. So now we look at another thing. So what we are now doing is to redefine what it means to be well-formed, okay? Remember well-formed formula? I'm going to redefine it now. So let's take a look at the new propositional logic system. This is a way simplified version. So we first start with omega 1, okay? Omega 1 is just negation. Just like before, because remember the subscript of omega indicates how many operands it requires. So the only operator in Boolean algebra that takes one single operand is negation. Okay, same as before, nothing has changed. But then how many operators that will take on two operands as a Boolean operator? Oh, we got and, we got or, we got implication, we got if and only if, at least 4, as discussed before. Now I say, forget all of those. We just have disjunction. Okay, so it's a kind of simplified way of expressing things. What about a well-formed formula? What does it mean when we have a well-formed formula? Well, we start with something that is not well-formed first, okay? So what we do is we have this predicate called is ADE. ADE is basically saying is a disjunctive element, okay? I just give it a name, okay? But what makes it a disjunctive element? Pick anything in alpha. What is alpha again? Those are all the symbols, right? 0, 1, P, Q, R, S, T, the variables. Those are all the alphabets that we play with. So by themselves, each one is a disjunctive element. Okay? I just call it a disjunctive element. Are we good so far? Yes? Okay. The next one says, the negation of something that is a disjunctive element is automatically also a disjunctive element. Okay? So that means the negation of P is a disjunctive element. The negation of Q is a disjunctive element, and so on. If you can find something in alpha, that something is a disjunctive element, the negation of that something is also a disjunctive element. Are we good so far? So there's no recursive definition. Now let's see what this means. This basically says, give me n disjunctive elements. What disjunctive elements are we talking about? Phi 1 all the way up to phi n. Okay? Is that okay? Give me a number of disjunctive elements. The or of all of those things is a well-formed formula. Are we good so far? And that's it. This is the whole definition of, the new definition of what is well-formed. Are we okay with this or not? Yep.
So how do you know, whether those two I's are independent or if they're related? Because one's, depending on the disjunction and the other's on the quantifier.
They are independent. So this I, the scope of this I is only on this side of the implication, and the I of this one is only on this side. Okay, so let's take a look at some examples, okay? So we'll look at an example of a typical alpha, okay? A typical alpha would be defined like this. We got 0, we got 1, because one is false and the other one's true. We got P, Q, R, S, T as individual variables, and leaving the schematas out of this whole thing. So if this is true, then 0 is a disjunctive element, 1 is a disjunctive element, P is a disjunctive element, the negation of Q is a disjunctive element. Is that okay? The negation of 0, which is not very useful, is also a disjunctive element. Are we good so far? Then what is a well-formed formula? A or of at least one of these items is a well-formed formula. Okay? So all of these are disjunctive disjunctive elements. So now we want to look at, well, what makes it well-formed? This is well-formed, is a well-formed formula, okay, by itself. Is a well-formed formula. P or Q is a well-formed formula. Not P or not Q is a well-formed formula, and so on. Okay? That's it. Yep.
Why are single elements well-formed? Is it just because if you had I going from 1 to 1, it would count?
Because you can always make it well-formed. So if this is well-formed, if you don't like this, make it false or false. You can always coerce it into, oh yeah, I can see the disjunctive operator, but without changing its meaning. Yep. So I just extend the definitions to say that that is also well-formed. So I don't have to always have that plus 0 when I have a single thing on that side. Okay? So is that okay so far? So are there any questions about, what makes a formula well-formed? Yes?
How would you get an element that wasn't disjunctive in the set? Would it just be something that wasn't in the set there? How would you get something that wasn't a disjunctive element?
Well, the entire universe of things that you can handle are only in this form. Now, but all of these things are connected by a implicit conjunction. Okay? So that means, what this means is, so let's say I have an iota. Okay, iota has the usual stuff, true is true, not false is true. And let's just say that I throw in something here that is also in the iota. But everything has to be well-formed, remember. Okay, so I can throw in something like P or Q into this whole thing. I can mention something like, R or not T, okay? So if this is iota, it is an implicit conjunction connecting all of these things, okay? So what this means is true is true, and not false is true, and P or Q is true, and R or not T is also true. All of those things are true at the same time. Everything in iota are true at the same time, and it's a given. Is that okay? But that's the only implicit conjunction that you have. So you might look at this entire system and think, well, that's pretty restrictive, okay? All those other things that we could express using implication and all the random ways of nesting negation and conjunction and disjunction and implication and equivalent. What about those things? This is very, very simple, okay? Seems to be very restrictive. So my conjecture, okay, without proving it in today's class, my conjecture is in section 5.2, I'm going to claim that if you give me any valid Boolean expression using all of the other operators nested in any legal way, there is a way to convert that so that I end up with a conjunction of all the well-formed formula. That's a pretty big claim, okay? Because what it means, I can give you one example before the class ends. We are on 20 right now, so I still can give you a little bit more time. Okay, so I can look at something like this, which definitely does not meet that requirement of well-formed, right? Because it has got implication, it has got negation on the outside of an operator, and all kinds of bad stuff, okay? But I'm going to tell you, give me any Boolean expression that is valid itself, I can convert it into a conjunction of disjunctive terms, or a conjunction of well-formed formula using my term used earlier. So it is just as expressive as the usual Boolean expression that you are familiar with, except the format is very simple, okay? So I'm going to end today's lecture at this point, and then we'll continue today's lecture next Wednesday, the Monday after next Wednesday. So we'll continue the lecture on Monday. The exam is on next Wednesday. So if you study over the weekend and you have any questions about the concepts, bring those questions on Monday so we can talk about it.